Welcome to Quideo 2. So the basic question has Professor Moore's times in minutes for his swim of 2,000 yards, plus his pulse rate after swimming in beats per minute for 23 sessions. So letter A, I want you to verify that the linear model is appropriate to model the data and state the equation of linear model. So in orange, there's the equation of a line. And in orange is the equation for the specific line, with this number being the y-intercept and this number being the slope. Then I have a graph showing the pulse rate on the y-axis and the time on the x-axis, a scatter plot of the data, and the R2 value being 0.556, which is a moderate correlation. Part B asked us to predict the professor's pulse rate with a time of 34.3 minutes. And then it asks us how accurate it is based on the actual pulse rate of 152. So to find this, you simply plug in 152 into the x, or you plug in the 3430 into the x, and you get this number. And then to find if it's accurate, you find the residual, which is the observed minus the predicted, which ends up being 4.6. So then it asks you how accurate it was. So the values don't deviate too much from the line. For example, when predicting the pulse rate value for a time of 34.3 minutes, the predicted value is 147.396. This value, 4.604, from the observed value, it was not perfect, but it wasn't too far away from the line. So part C wanted us to predict the swimming time. So in order to do that, we must rearrange the equation. So this is the first equation. We're going to rearrange it in terms of x, which is this, and then we simply plug in the values. And it's written like this or like this, and then we get this number. And this number is actually very close to the actual number, and it's not, so it's when you find the difference, it's actually not too far off, which means we have a pretty good LSRL. So for part D, it asks us to explain clearly to someone who knows no statistics why there needs to be two different regression lines for part A and part C. So there has to be two different regression lines because you're finding two different variables based on the given variable. The y== equation gives the pulse variable in the problem, and you need to find time, whereas the x equation finds the time when you're given the pulse. Okay, then for the advanced question, it gives us some data about hard drives and the capacity on them and the price. And it asks us to, without a calculator, write the regression equation and define the variables. So we're going to have x equal the capacity and y equal the prices. So our equation looks like this with the predicted value. This is the y-intercept and this is the slope. So the regression analysis gave the y-intercept and the slope, which can be found right here. And the slope, as we know, is always over that. Okay, then part B asks us to explain the meaning of the slope and y-intercept in the context, which I have here. Then for part C, it asks us to predict the price of 3.0 TB drive, which is again talking about the capacity. So we just simply plug it in and chug, and so we get 330.404, which is in dollars for that amount. And then it asks us if he paid $300 for it, would it be a good price to pay? And if he paid $300 for it, it would be a good price because we just found in part C a number that would be predicted for it, which is actually $30 more than would be found. So the AP question has us looking at a computer-generated table here. So we have, we immediately see the y-intercept for the electricity produced and a slope for the wind velocity, as well as an r-squared value. So part A asks us to use a computer output, which is this, above to determine the equation of the least squares regression line and identify the variables. So we literally just plug these two values in right here. So we determine that x is the wind velocity and y is the electricity produced. So we simply plug it in, leaving the predicted and the x. Part B asked us how much more electricity would the windmill be expected to produce on a day when the wind velocity is 25 miles per hour than on a day when the wind velocity is 15 miles per hour. So to solve this, you simply, x is wind velocity, so you plug in 25, 15, and you get out 6 point whatever and 3 point whatever, and then you simply subtract them to get 2.4, and we have to remember our unit, so the 2.4 is in amps, so the wind that is 25 miles per hour or 25 miles per hour produces 2.4 more amps than the wind that is 15 miles per hour. So part C asks us what proportion of the variation in electricity produced is explained by the linear relationship with wind velocity. So this is just saying that the proportion of the variation in electricity produced is explained by its linear relationship with the wind velocity, because it really just wants to know the r-squared value. And if we look up here, the r-squared value is 0.873. So we got to remember that when it's asking for proportions, sometimes they want a percent of values that are close to the regression line, which is also known as r-squared, and we want our r-squared value to be close to 1. That wraps up our Unit 2 video.